components of learning. So now I would like to abstract from the learning problems that I see, what are the mathematical components that make up the learning problem? And I'm going to use a metaphor, okay? So I'm going to use a metaphor now from another application domain, which is a financial application. So the metaphor we are going to use is credit approval, okay? You apply for a credit card, and the bank wants to decide whether it's a good idea to extend a credit card for you or not. From the bank's point of view, if they are going to make money, they are happy. If they are going to lose money, they are not happy. That's the only criteria they have. Now, very much like we didn't have a magic formula for deciding how a viewer will rate a movie, the bank doesn't have a magic formula for deciding whether a person is creditworthy or not. What they are going to do, they are going to rely on historical records of previous customers and how their credit behavior turned out, and then try to reverse engineer the system, and when they get the system frozen, they are going to apply it to a future customer. That's the deal. So what are the components here? Okay, let's look at the, first you have the applicant information, and the applicant information, you look at this, and you can see that there is the, the age, the gender, how much money you make, how much money you owe, and all kinds of fields that are believed to be related to the credit worthiness. Now, again, pretty much like we did in the movie example, there is no reason that these fields are related to the credit worthiness. They don't necessarily uniquely determine it, but they are related. And the bank doesn't want a sure bet. They want to get the credit decision as reliable as possible. So they want to use that pattern in order to be able to come up with a good decision. Okay? And they take this input, and they want to approve the credit or deny it. So let's formalize this. First, we are going to have an input, okay? And the input is called X. Surprise, surprise. And that input happens to be the customer application. So you can think of it as a d-dimensional vector. The first component is the salary, years in residence, outstanding debt, whatever the components are. You put it as a vector, and that becomes the input. Then we get the output Y. The output Y is simply the decision, either to extend credit or not to extend credit. It's +1 and -1. Okay? And being a good or bad customer, that is from the bank's point of view. Okay? Now, we have, after that, the target function. The target function is a function from a domain X, which is the set of all of these. Okay? So it is a set of vectors of d dimensions, so it's a d-dimensional Euclidean space in this case. And then the Y is the set of all Ys. Well, that's an easy one because Y can only be plus or -1, accept or deny, and therefore this is just a binary codomain. Okay? And this target function is the ideal credit approval formula, which we don't know. In all of our endeavors in machine learning, the target function is unknown to us. If it were known, nobody needs learning. We just go ahead and implement it. But we need to learn it because it is unknown to us. So what are we going to do to learn it? We are going to use data, examples. So the data in this case is based on previous customer application records. The input, which is the information in their applications, and the output, which is how they turned out in hindsight. This is not a question of prediction at the time they applied, but after 5 years, they turned out to be a great customer. So the bank says, okay, if someone has these attributes again, let's approve credit because these guys tend to make us money. Okay? And this one made us lose a lot of money, so let's deny it, and so on. And the historical records, there are plenty of historical records. All of this makes sense when you are talking about you have 100,000 of those guys. Then you pretty much, you say, okay, I will capture what the essence of that function is. So this is the data. And then you use the data, which is the historical records, in order to get the hypothesis. The hypothesis is the formal name we are going to call the formula we get to approximate the target function. So the hypothesis lives in the same word as the target function. And if you look at the value of G, it supposedly approximates F. While F is unknown to us, G is very much known. Actually, we created it. And the hope is that it does approximate F well. That's the goal of learning. Okay? So this notation will be our notation for the rest of the course. So get used to it. The target function is always F. The hypothesis we produce, which we refer to as the final hypothesis, will be called G. The data will always have that notation. There are capital N points, which are the data set. and the output is always y. Okay, so this is the formula to be used. Now let's put it in a diagram in order to analyze it a little bit more, okay? So if you look at the diagram here, here is the target function, and it is unknown. That is the ideal approval, which we'll never know, but that's what we are hoping to get to approximate. And we don't see it. We see it only through the eyes of the training examples. This is our vehicle of understanding what the target function is. Otherwise, the target function is a mysterious quantity for us. And eventually, we would like to produce the final hypothesis. The final hypothesis is the formula the bank is going to use in order to approve or deny credit, with the hopes that G hopefully approximates that F. Okay. Now, what connects those two guys? This will be the learning algorithm. So the learning algorithm takes the examples and will produce the final hypothesis, as we described in the example of the movie rating. Now, there is another component that goes into the learning algorithm. So what the learning algorithm does, it creates the formula from a preset model of formulas, set of candidate formulas, if you will. And these we are going to call the hypothesis set, a set of hypotheses from which we are going to pick one hypothesis. So from this H comes a bunch of small h's, which are functions that can be candidates for being the credit approval. And one of them will be picked by the learning algorithm, which happens to be G, hopefully approximating F. Now, if you look at this part of the chain, from the target function to the training to the learning algorithm to the final hypothesis, this is very natural, and nobody will object to that. But why do we have this hypothesis set? Why not let the algorithm pick from anything? Just create the formula without being restricted to a particular set of formulas, script H. There are two reasons, and I want to explain them. One of them is that there is no downside for including a hypothesis set in the formalization, and there is an upside. So let me describe why there is no downside, and then describe why there is an upside. There is no downside for the simple reason that from a practical point of view, that's what you do. You want to learn, you say, I'm going to use a linear formula, I'm going to use a neural network, I'm going to use a support vector machines. So you are already dictating a set of hypotheses. If you happen to be a brave soul and you don't want to restrict yourself at all, very well. Then your hypothesis set is the set of all possible hypotheses. Right? So there is no loss of generality in putting it. So there is no downside. The upside is not obvious here, but it will become obvious as we go through the theory. The hypothesis set will play a pivotal role in the theory of learning. It will tell us, can we learn, and how will we learn, and what not. Therefore, having it as an explicit component in the problem statement will make the theory go through. So that's why we have this figure. Okay, so now let me focus on the solution components of that figure. What do I mean by the solution components? If you look at this, the first part, which is the target, let me try to expand it. So the target function is not under your control. Someone knocks on my door, he says, I want to approve credit. That's the target function. I have no control over that. And by the way, here are the historical records. I have no control over that, so they give me the data. And would you please hand me the final hypothesis? Okay, that is what I'm going to give them at the end before I receive my check. Okay? So all of that is completely dictated. Now let's look at the other part. The learning algorithm, let's get it back to, the learning algorithm and the hypothesis set that we talked about are your solution tools. These are things you choose in order to solve the problem. And I would like to take a little bit of a look into what they look like and give you an example of them, so that now you have a complete chain for the entire figure in your mind, from the target function to the data set to the learning algorithm, hypothesis set, and the final hypothesis. Okay, so here is the hypothesis set. We chose the notation script H for the set, and the element will be given the symbol small h. So small h is a function, pretty much like the final hypothesis G. G is just one of them that you happen to elect. So when we elect it, we call it G. If it's sitting there generically, we call it small h. Okay? And then when you put them together, they are referred to as the learning model. So if you are asked what is the learning model you are using, you are actually choosing both a hypothesis set and a learning algorithm. We'll see the perceptron in a moment. So the perceptron, this will be the perceptron model, and this will be the perceptron learning algorithm. This could be neural network, and this would be back propagation. This could be support vector machines of some kind, let's say radial basis function version, and this would be the quadratic programming. So every time you have a model, there is a hypothesis set, and then there is an algorithm that will do the searching and produce one of those guys. Okay? So this is the standard for the solution. Now, let